that really the way planets are going to potentially care about external photoevaporation depend upon the times at which both processes happen. If your planets are going to form way before the external photoevaporation does anything, which could well happen, well, then it's not really a very important process. Whereas if the external photoevaporation happens on a comparable timescale or even quicker, then it's going to be important for the planet formation. So am I going to have to shout next slide? Could I have the next slide, please?
Well, Tom, can you try just one quick thing? Can you click request control?
Where's that then?
Above the slides. If you see
it's blacked out for me. Yeah, so I think we'll just have to deal with
it. No worries.
So what we wanted
just tell me next slide.
Will do. What we wanted from this talk was to understand how external photoevaporation is currently included in planetary population synthesis models. So calculations of how disks evolve with a bunch of different ingredients to try and predict planet populations, like you can see on the right here. And we want to understand how the external photoevaporation is treated and maybe what could be done to improve that in the future. Next slide, please. So what I've done here is, as I said, in the last 48 hours, tried to bring myself roughly up to speed with what is done. And I'm sort of picking on Christoph and his group and taking that as the standard. So I've been reading some of their papers in the last couple of days. And I think it's fair to say that the bottom line in these population synthesis models is that external photoevaporation is there primarily to set the disk's lifetime. We observe disk lifetime, so this acts as a controlling mechanism to make sure that these population synthesis models get something similar. And this can indirectly affect, it does affect the final mass you get for giant planets because it affects the mass reservoir that you have for them to accrete from. So next slide. So that's the role of the external photoevaporation. And I've gone into a bit more detail than I normally would in a talk about how the external photoevaporation is actually handled. So it's following Matsuyama et al. 2003. And roughly what happens there is you have a star with a disk. You can see the circle with the little triangle. You've got to deal with my terrible drawings without a cursor. Yeah, there you go. And that's being shone upon and materials being driven away from it. And if the heated material was all, say, 1000 Kelvin, as you go further out in that heated region, at some point, the material will be unbound from the star. And that is at this gravitational radius Rg. So that's given by the gravitational constant times the star's mass divided by the sound speed squared. And that sound speed squared is just related to the temperature. So external to that point, you'd expect material to be able to escape the star. Next slide, please. But in reality, there's actually material can escape from further in, from what is called the effective gravitational radius. And that's because you have pressure gradients, which can help give material a kick out of the system. And then next slide. There's quite a lot of little transitions. So what is done in these models is interior to that effective gravitational radius, the surface density does not change due to external photoevaporation. And external to that, it changes according to this equation at the bottom here, which if we now jump to the next slide, I will describe in a bit more detail. So if I've understood it correctly, what you have is a disk here again, and there is that equation. What it's telling you is how the surface density changes over time across that whole region between those two dashed lines due to some imposed external photoevaporation rate. So in that equation at the bottom, the pi r max squared minus the other term is just the area in the disk of that region between the dotted lines. And m dot wind is a parameter, which you can just choose whatever it is, and it's chosen to reproduce the right kind of disk lifetimes. Next slide. So if you have a smaller disk, the surface density change at any given radius is the same as it was when the disk was big. But the area of the disk is smaller, so the mass loss will drop. So next slide again, please. So I think this could be wrong, but if I've understood correctly, this is how the mass loss rate would be changing with disk size. And then next slide, please. So what I did was, again, read through some of these papers. This is all in the last 24 hours now, pretty much, and look at what the distribution of mass loss rates is. So the blue distribution here is what is chosen to set that m dot wind parameter. So it's got a mean of 10⁻⁶ and a standard deviation of 0.5. But that is for a disk that is 1,000 AU in size, and as the disk truncates, that distribution of mass loss rates also goes down. And so that orange line is for a 100 AU disk. So you can see now the mass loss rates are pretty small. Next slide, please. So what I really wanted to get from this, what was going to be a review talk, was to ask things like, well, what might be missing from this kind of prescription? There's no time dependence of the UV field. There's no sensitivity to the disk's mass. The only way that it cares about the star's mass is that gravitational radius moves in or out. And can we do better? And is it actually worth trying to do any better? So Andrew discussed a whole bunch of these other new approaches to working out mass loss rates in recent years. But they're relatively hard to implement. So is it worth the effort of putting those in, or will it just be a lot of work for not much difference? Next slide. So again, last 24 hours, I thought I'd have a quick comparison of some of these more modern mass loss rate prescriptions with what is done in the population synthesis models. So I've just taken a very small subset of this fried grid. So in this plot, we've got the disk radius on the y-axis and the mass on the x-axis. And the points are a bunch of different fried grid models. So it tells you the mass loss rate, which is what's in the color bar, for a disk of that mass and that size. And these are around a solar type star. This is just a small subset of the grid, and it consists of about 4,000 models spanning different UV field strengths and stellar masses and stuff. So if we go to the next slide, we're nearly done. So what's on the right here is a comparison of this sort of population synthesis approach mass loss rate as a function of the disk size. So that's what the black line is. That's for the peak of that distribution of mass loss rates that people consider. So the right-hand side plot, sorry. That black line is the mass loss rate that you'd get for a disk of a certain size. So as the disk gets smaller and smaller and smaller, the mass loss rate goes down, and then you hit that beta RG and it plummets to 0. And then the points are the fried grid mass loss rates for a solar mass star of different sizes in a 1,000 G0 radiation field. And the reason you have lots of different points at any given radius is just due to the mass sensitivity of the mass loss rate, which isn't accounted for in the population synthesis models. The plot that was on the left is showing from Fatuzzo and Adams, the probability that a star is exposed to a given radiation field. And so the red vertical line is showing you what these models are, the blue points here. If you go to the next slide, we're now at a factor 10 weaker UV field. And so it's moving down towards more where the population synthesis models sort of sit. And then next slide again, factor 10 weaker again still. We're now entering the tail of this probability distribution on the left. So it's not a very common UV environment. And you can see it's still sort of maybe evaporation can do more than it is expected in these population synthesis models. So I'm not saying that fried should be included. It's a possibility, but maybe it's hard work. But I think it's worth having a think about the role external photoevaporation plays in these population synthesis models. And then one more slide I think I have. And if you don't want to stick something like fried in your population synthesis model, what you could do is flip the question around and say, well, what happens if I just take my m.wind parameter and just bump it up on higher and higher values? At what point does it affect planet formation beyond just setting the disk lifetime and the mass reservoir that giant planets can accrete? How strong an effect does the external photoevaporation have to be to affect your inner planets, for example? So final slide, please. It's a bit of a whirlwind sort of tour of the topic that's been quickly pieced together, but I hope you take away the rough idea. We wanted to know how external photoevaporation is put in these population synthesis models. So, it's this Matsuyama thing that I've tried to quickly summarize, and maybe, have a look at how it compares to some more modern stuff, and, ask what there might be to do here in the future to understand just how external photoevaporation might be affecting planet populations. So I hope this will be a topic for discussion later. And if there's any questions now, we can also maybe have a little chat.